This is the result of a recent reaffiliation. I'm now the CTO of Trinity Biocarbon, which is located out of Cairo, Egypt. But let's go back a little bit and see where this all started. So here we have, and I can't tell whether the pictures are blocking that accurate depiction of me on the right, but you can see an almost noticeable aging phenomena that has occurred in the last 15 years in biochar, but that's to be expected. But my point here is really I've been doing this for a long time relative to the biochar world, but prior to that, I spent 30 years working in activated carbons. My background is chemistry and chemical engineering, so I have the training and then I had the experience and time to get into this material in real depth. And so I've got some insights. Whether they can be trusted or not remains to be seen. Uh, my first stab at this particular area was trying to characterize biochar properties in a manner that let me compare different biochars to each other, maybe substitute one biochar for another with less change in performance, etc. And I did participate in the IBI characterization regime program back in 2012. Until I quit in protest one day because they were insisting on using ASTM methods across the board. And I attempted to explain that if biochar is a new material, you can't use an old test designed to measure something in a different material and expect it to come back with the answer that's relevant to the material biochar. It's relevant to the other material. But that fell on deaf ears, and we're fighting that battle to this day. But here's a history of some things. This may be a way out. I don't know. I am excited about this instrument I developed, and it grew out of this esoteric title, Schenkel and Shenzhou Revisited. And in that paper, we used this particular device, which is the original GACS machine that I had developed for studying activated carbons over the years. And I didn't really invent it, to be honest. Like all good researchers, I basically either borrowed it or stole it from Calgon Carbon and created a different version. Theirs is called Tactic. It's an internal device. It's $250,000. It's very accurate, very expensive, and doesn't have any people running it. Mine has a person running it and is substantially cheaper. And the principal phenomena we demonstrated in Shenzhen and Shenzhou was to recreate the conversion curve, the yield curve, the blue line, which was Schenkel's contribution, which shows up in Antel's The Art, Science, and Technology of Charcoal. And then the second phenomena, which is this phenomena of absorption or surface area rising from 300 to about 600 and then falling again afterwards. And that was a very interesting phenomena, and one that I think is relevant to the current industry-wide sort of mania to go to higher and higher carbon contents, lower and lower H over C organic levels, and doing that by going to higher temperatures. And we run a risk of collapsing a very critical property of the biochar, which is basically its microporosity. At some point, the house of cards falls apart, and the material literally collapses onto itself. It absorbs itself, and then you destroy the micropores. So too much of a good thing when it comes to heat is actually true. So in this study, that phenomena, that rise and fall, I reproduced this in some laboratory data because that Schenkel and Shenzhou dates from 2010. I went back in and took some wood pellets and ran some very, very controlled experiments and reproduced a homologous series from 350 to 800. And here we see as we go up in the temperature of the HTT, we see a rise in the absorption across the range of temperatures. So the way this assay works is you heat the material up, dry it out, get rid of the moisture, take it up to 300 degrees C, in nitrogen, then you flip from nitrogen to what's called a challenge gas. And that challenge gas in this case is R134A, which is the refrigerant used in automobile air conditioning systems. It is a readily available material. It does have a greenhouse impact, but you're only using grams per assay. And the nice thing is it doesn't burn, but it's also a very difficult to absorb material. So we get very good sensitivity, and it's a heavy material. So we note here between 350 and 600, we see the absorption rising, which is where the curves move from the lower left to the upper right. And then when we go beyond 600 and to excess temperatures, we see the deterioration of the curve. And we attribute this to the collapse of the micropores. And we have additional data to reinforce that. But something goes wrong. So in the process of joining Trinity, I was asked to create this capability for them in Cairo, because they're commissioning a large-scale production capacity, which will come on eventually this year sometime. And that gave me an opportunity to revisit designing this device to see if I couldn't take some of the cost out, because the original devices were quite expensive because of the balance, really. And also try to make it a little more automated so that the amount of operator interaction was reduced. And it also gave me an opportunity to document the construction process in discrete steps. So that created this device we see on the left. It has the finest and most cost-effective of the latest version of Chinese analytical balances. And compared to my $10,000 balance that I used way back in 2010, this $250 balance does astonishingly well. And the test is really designed with a fairly large sample. It's essentially a macro TGA. And that allows us to get good signal to noise ratio. Having said that, I want to note that biochar is a difficult material to assay. It has a lot of different properties. It has tars, it has fixed carbons, it has volatiles, it oxidizes over time, it readily takes up moisture, and all these things prevent you from having, lots of significant figures in your results. So I think we need to not squeeze the data. We use this as basically a device to compare one char against another. Although with time, we'll probably get enough data to start making some good correlations. It's a particularly valuable device, in my opinion, for a production facility who could make a change and wait, for a couple of residence times and then take a sample and go in and see what impact it had on the carbon. And we'll see in a few minutes what kinds of things we're measuring. On the right-hand side is the actual measuring cell. What it consists of is a small basket of fine mesh screen, stainless, that's hung beneath the balance. And we cover the top of the balance so there's no interference there. And basically, we're weighing that little basket. And we seal that basket into a heated chamber that we purge from below with either nitrogen or the challenge gas. It sweeps out that hole in the top, and that allows us to measure the weight at any interval we want, typically every half a minute. And it allows us with that probe that appears to stick down in there beneath those three equivalent positioning posts, the temperature right above the bed of charcoal, of biochar. So we fill that basket right up just underneath that thermocouple. We flow gas up through the sample. We weigh the sample at all times, and we get the downstream temperature of the sample. And that's a lot of data against time. So, the three things in this world that we measure very accurately are time, weight, and temperature. So this device, the TGA, really exploits that phenomena, and it allows us to then get insights as to how the sample reacts to temperature changes and also to atmosphere changes, because we control the atmosphere either to a challenge gas to see absorption, or in one assay, we actually flip to air to see if there's a self-heating phenomena that we need to be aware of. Some of the upgrades from a previous design, I had a previous publication that was out there but not terribly popular called GACS on a Budget, and it used a video camera to video camera the temperature and the balance, and then you hand scribe the data onto a spreadsheet. Very tedious. Now we have a temperature controller. They're very convenient, a little hard to program, but once you get them right, they do the same thing time and time again. And it's a ramp soak controller, so you can give it take it from one temperature to another over a period of time you specify, and then keep it at a temperature and go on to another one. It's really takes a lot of the repetitiveness out of these assays. It makes them very consistent. Lower left is the gas controls. We switch the gases. We do that very rarely, once or twice in an assay. And that's done manually. In the center, we see this custom heated thermal chamber, which is a piece of simple pipe, that we cap and we wrap the gas goes in that 1/8-inch stainless tube, goes around with the outside of the heated chamber and then is inserted in the bottom. Upflows from there. The heat tape is controlled. It's only about 250 to 300 watts of heat going in. So it's not a big current draw, not putting a lot of heat into the lab, but it gets that very small zone around that sample accurately controlled and measured. And then we see again the basket, and the chamber's open. Basically, we have a jack stand that pushes the chamber up. The heated chamber is encased in this case, a tomato can of tomato stews or something. So yeah, it's pretty low key, pretty grad student stuff. It's not automated, but it's great. Creates some great data. And this is what this machine does all by itself, not all by itself, but this is what it's capable of doing. We basically took some of the challenges of working with biochars, and again, I've worked with them for 15 years. I've sampled thousands of different biochars, and one of the challenges is drying them very accurately. They don't dry at 104 degrees C. I'm sorry, they just don't. There's absorbed moisture that doesn't come off, and so we define into this test a ramp. The red line is the temperature ramp. It's referring to the temperatures on the right-hand side. So we ramp up to 150 degrees C, the recommended temperature for driving off the moisture, absorbed moisture, and we hold it until we have a stable weight. And then we ramp up to 300 degrees C, and we hold that for about an hour. And we defined the weight loss that comes off at 300 degrees C as the VOCs, just an arbitrary partitioning. We say up to 200 is water, up to 300 is going to be the VOCs. We actually cut it between 200 and 325 because it's easier to capture that time. And then we go up to 450 for another hour. And we call those semi-volatiles. Now, I don't know that these partitionings are particularly accurate and definitive, because you have a spectrum of absorbed materials, organics in there. It's almost a continuum of spikes when you GC this stuff. But it's an interesting way of carving the things on the biochar into a couple of groups. First off, getting the water out of the way. Second off, defining VOCs. Now, let's imagine that VOCs are that portion that desorbs in that first growing season and takes up some nitrogen. It's a source of sugar for the microbes. And then let's suppose that SVOCs are the biochar, non-graphitic biochar components that slowly desorb over the century. So not fast enough to alter the growing season of only one crop, but eventually lost back and carbonized back to the atmosphere. I don't know that I've only done this for 6 months. I'm working with it. I'm very happy with the repetitiveness of the assays. And there's a spectrum of actual weight losses there, and they correspond to the most stable, the lines up towards the top. They are the higher temperature chars, and then your lower chars that you'd expect to have higher VOCs and higher SVOCs show substantially greater weight losses over the course of this assay, which takes about 3 hours. Now, an additional advantage of this is you can, on the way down, once you get done on the right-hand side, you can also do and switch your challenge gas, and you can do the gravimetric absorption capacity scan of the devolatilized biochar and compare that. And that has some insights that we'll see. The device also has the capability of going to 500 degrees C and accurately measuring the ash content, because basically at 500 C, you don't burn off all the carbonates, you don't decompose them to calcium oxide, which is what happens above 600, which I think was the pH issue in the prior talk. And so it's a convenient way of plugging it into a machine and getting a good ash reading. So I wanted to test it against some known chars, and one of the set of chars that I used was a char I had modified by a technology that I've been developing over the years under a company named AC Fox. There's a patent on it, and if people have high tar chars that they want to strip the tars out of, this actually does it very nicely. Someone who's interested in that should look this patent up, and someone that's interested in the technology should contact me with the email at the end. And somebody that wants to buy the technology should just, send a blank check and we'll go from there. But here's what I wanted to show you. I use this technology, I use this method, this assay, to compare two chars. One is the bottom char, the green char, which was the bulk standard kind of low temperature char, very low absorption. The below that yellow line, and that gets into the weeds. And in the course of the AC Fox treatment, it moved that line up to the red line in the center. So that blue arrow showed you the change imparted by treating it in AC Fox conditions, which were something like 300 to 400 degrees C in a flow of air. So not allowing combustion, but allowing oxidation of the tars. And then, because you can do the GACS test on the way back down, I show you that the green line was upgraded to that blood red line, and then the red line was upgraded to the blue line. So we're seeing the kinds of changes we expected. And this is what the GACS, this is what the instrument records. So you're seeing the temperature on the right-hand side and the weight losses. So this is one of the simpler ones, and I'll start moving quickly through these because, again, someone that listens to the talk again can stop. But you can see the weight loss, the drying at 150, and then you take it up to 300. The blue line is when we switch from nitrogen to R134A, and as we descend, we see the rise in the weight, and that becomes the uptake. It's a little more complicated when you have the stripping steps, but we again see the drying at 150 on the red line, where we saw it up plateauing up in the purple line, and then we see the weight loss as we go through 300 degrees C. It's an ongoing stripping. I don't know if it ever asymptotes out and stops because there's a continuum of desorbed materials to be stripped off. I'll note as a chemical engineer, this is a very aggressive stripping environment. This is bone dry nitrogen at 300 degrees C and about a 50-to-1 volume advantage on the nitrogen side. So the solids are being stripped aggressively by this nitrogen stream at a temperature. And then similarly, we go to 450, a great loss there, and then the rise back up is what we're measuring. People can go back and compare these, or if you contact me, I'll provide the data, and we can see the same kind of phenomena. This is interesting because for some odd reason, the operator failed to switch the R134A at the proper time, the operator being me. And you can go back in and just reheat it up above 300 and then catch your absorption scan. So it's forgiving in the sense that you can get your data when you want your data. This is the summary of the phenomena, the changes we saw. I show you the absorption change, but then we see the different amounts of VOCs and SVOCs that are stripped out as we upgrade the material with both the AC Fox process and also the impact of stripping. The minus SVOC is what the SVOC logo means. So we're getting, we're getting the kinds of results we expect. Now, are they quantitatively predictive? No, not until we have much more data. I looked then at that homologous series where we increased the temperatures and came back down. Here is the phenomena. What we see is the absorption capacity going through the maximum and dropping back down. The SVOC version is the stripped versions. They have less importance. It's interesting that the initial rise in absorption appears to be due to the removal of the VOCs and the SVOCs, but by the time we get to 600 degrees C, they're quite low. And the subsequent higher temperature materials, they're lower yet. And so the collapse of absorption capacity cannot be attributed to the TARs and the VOs in the char. So it's good insight. We don't understand this very well. So we need more data. Couple of quick pictures to look at it. This is the underhanging point on the balance. You then screw in a little tiny screw, the smallest one they sell at the hardware store, called an M3, and that becomes your underhook balance. You build a base, and I have written up these instructions. This is vermiculite. It's a great insulator also, and that's what I use to insulate the base to get the temperature right. And you put it all together, and these are the kinds of things that you can measure on the sample and measure quite repeatedly. And I find this to be it's more convenient, and it's very, very insightful as to the char. So, long story, we're now presenting this to the world. I've written up some instructions on how to build your own. I've given it to a couple people. They're not getting very far with it. I need some feedback. But if you're interested in going down this possibility, please contact me at the email that's there. Maybe eventually it'll show up under a search of a GACS Plus instrument. I'm considering making a couple of kits where I build everything but the bricks and mailing them to me. So if you're interested in buying all the parts but a couple of local cement blocks, also indicate that in an email. And that is all I needed to show you. So I can get out of this and give it back to Christian. Or he can take it back. I think he does that.
No.
I have to let it go?
Yeah, you have to let it go.
Well,
If you
this
want
is
to, otherwise you can
a
use
very
it on.
dangerous situation where I have sort of control over the future of humanity. So I welcome questions, and I also welcome inquiries both online and follow up. So thank you for the opportunity.
So thank you very much, you. I mean, I knew the instrument before, so because we had some discussions about it. The floor is open to questions. So you got the first one during the presentation, not so much about the GACS instrument. But I will ask it as the first one so that people get some time to write other questions. So let's say we have a biochar that has a relatively high surface area and optimized pore distribution. Do you have comments on post-quenching storage of final biochar in sub-zero degree temperatures and the effect of water freezing on pore integrity? So very specific question.
I have very strong opinions which start with the concept of surface area, which is totally irrelevant in a microporous material. But that goes back to the people who invented the method, and they said don't use it for microporous materials. And of course, the carbon industry went forward. The actual effect of water in biochar and freezing temperatures is really to shatter the particle, but it has virtually no impact on the microporous distributions and structures because they are much too small and much too strong. The smaller you get, the more the graphene suddenly becomes the strongest, stiffest material around. And there's really not a way in a micropore. And a micropore only has about 200 water molecules in it, very tiny. And it doesn't expand enough to shatter a micropore. So you don't have that mechanism occurring. There's a tendency in the biochar world to take SEMs, scanning electron microscopes, say, look at the pores. Well, you're not seeing the pores, the micropores. You're seeing the structure of the plant having been carbonized. So no, there isn't really any change in a freeze-thaw situation. Biochar, until you start really hitting it with some very aggressive oxidants, and we're not talking about air, we're talking about, ozone and things like that, is not going to change. The tars do react. The tars become oxidized very slowly. They leach out, etc. But now don't worry about it. Leave it outdoors.
Okay. Thanks for that comprehensive answer. So maybe if there's no question from the audience, I would ask my question, which is for the GACS absorption measurements. So do you already look at do you use it as a quality management for production, or what's the intended use?
Well, I think what you're doing is you're directly measuring core properties of the biochar. That is relevant to the marketplace. It's relevant to comparing biochars. Keep in mind, absorption is the principal mechanism for detoxification, and it's also the principal mechanism for desiccating moisture retention. So the last bit of moisture is the absorbed moisture that comes off. So these are important properties to compare one biochar against another. But the people in production need to know if the feedstock changed, or if they need to then rechange how they run their rotary kiln or something like that. If they want to make the same product day in and day out, and they've got variable feedstock coming in, they need to be changing how they make it to chase that optimal goal. So yeah, in production, it is invaluable. It's almost worthless to send a sample off and get a number back 2 weeks from now and be told, guess what? You were doing it wrong. The feedback loop is very reasonable for a production process where you may make changes once every 8 to 12 hours if you change at all. So you pull a sample, go in, have it run, and the foreman looks it over and says, I think we're going to slow it down 5%, give it a little more time because we're not getting enough absorption on it. We're leaving too many tars in it. And again, this assay shows you the tars, it shows you the absorption, it dries it correctly. It really fills in a lot of the specifics of an actual sample.
So the floor is open to questions. I know it was a lot of information in the presentation, so you might have to watch it again.
I think of all my talks, Christian, you have to admit that was the most coherent. I mean, some of my talks in the past have been really, brutal.
Yeah. Just the concept of the GACS measurement, I think, is the other way around than what people are expecting.
Well, I think we are suffering from a set of measurements where it comes down to volatile matter done at too high a temperature to be relevant to the material that started out, and surface area, which is a very problematic insight, a single-digit number to characterize a spectrum. So, I've spent a lot of time putting together the alternatives to, sending it to a lab and getting numbers back. And I think this is going to give you a better feel. This is how I look at biochars. And I've looked at a lot. So this is where I'm going, is to try to get some good data to build understandings around.
I think that's a great statement, because we are also end statement, because we are also perfectly on time. 4 p.m.
I have a last comment, which is I have this homologous series of absorptions and the tar levels. I would love to collaborate with someone who has the ability to do H/C organic or some of the other characterization methods that we're currently using to define char properties. I can send them those samples in exchange for the results. I can't pay for these results because I don't have a research budget. But if there's someone out there that wants to collaborate, I know how to make these chars and do my end of it. And I'd love to work with someone to fill in the correlations to some of the other more standard measurements, including everyone's favorite magic angle spinning NMR, which tells me, exactly what I need to know about the biochar.